Okay, so the title is written there, so I will not read it again. But just during the introduction, I was thinking about something else. Sometimes your thoughts are drifting somewhere, far, and then it came to me somehow that the previous series of talks was about forced liquid films, and now this is a different kind of forcing, because you have some traveling thermal waves, and people may think that these people from the Middle East, they are very kind of forceful and always use force. Well, let me stick to this. Anyway, okay, so I'm going to talk about the topic which is shown there. And first, I would like to thank first my collaborators, Professor Alexandr from Georgia Tech in Atlanta, US, and his student, Wendy Mao. And also, the most important part of this research, funding from the binational US-Israel Science Foundation. Okay, so for several years already, we will be thinking about how to move thin liquid film from point A to point B without using too brutal force. For example, if you have a thin film and you want to pump it or to move the liquid from one location to another location, of course you can induce a pressure gradient and just force it from point A to point B, but because of the fact that films are very thin, okay, so to overcome this viscous stress, you must apply very large pressure gradient just to be sure that it moves, to create sort of net flow rate in a certain direction. And then, well, some liquids would not like it. For example, if you want to move DNA from here to there, from the place where it's taken along the surface, along the substrate, to deliver it to the location where it's been analyzed, so it may be damaged just by a large pressure gradient. Okay, so what else? And then, while thinking, we came across the experimental paper by Howard Stone and George Whiteside in Harvard. I'm talking about 2003. Oh, it's already a decade, wow. Okay, so Stone was then still in Harvard before moving to Princeton, and he's a there student. Actually, there was one more, I probably forgot to put it. Anyway, what they did is the following. Imagine a solid substrate, but the solid substrate now, somehow it doesn't work. No, here it works, and there. Do you see anything? Oh, okay, now I see. Okay, imagine you have a substrate which is not flat. And, okay, so now if you put a liquid film here on top of it and hit the surface from below, and even imagine then that the substrate is perfectly conducting. Okay? So basically, because of the topography of the substrate, the temperature here along the substrate, along the contact line between the liquid and the solid, is not uniform anymore. So then you think that something may happen, something abnormal may happen. Okay. And what they did is the following. So they put a film here on top of this surface. That's exactly something like here or like here. And they hit it from below. What happened is the following. There were several instances that the film, some flow emerged inside the film. And in some cases, the flow field was something like this. So which means one period or the domain which occupied one wavelength of the substrate developed a sort of a picture or structure like this, so which means that two circulating cells emerged in one period. Okay, in some other cases, and actually they even quantified this, they said, okay, if LP is, lambda P is a period of this surface structure, so then if the film is around 1/2 of this lambda P thick, then this structure prevails. Now, if they put, when they put a thicker film of a thickness in the order of lambda P itself, of the periodicity of the wall, so then they saw something else. So the whole, instead of 2 cells per period, they got 1. Okay. And then, actually, they played with the temperatures, with, more precisely with the temperature difference between the substrate and the outer air. And what they found, it was actually remarkable. Actually, this is a shadow graph, a picture of both cases. And actually, the brighter shades correspond to the upwelling flow. And there the temperatures are higher, and the darker shades correspond to flow directed downward, and where the temperatures are low. And to their kind of big surprise, I would imagine, when they used a left-right asymmetric substrate, okay, so they got a net flow. So in this case, well, there is a flow to the right, there is a flow to the left, but there is a net flow which is directed in the direction of this arrow going to the right. In this case, it was a net flow going to the left, and this was kind of remarkable. Okay, now let's look at this graph. Now this graph shows you this axis is just delta T, the temperature, a temperature drop between the temperature here on the underside of the substrate, and the temperature somewhere far above. Okay, so this is the temperature. Don't be afraid about 130 degrees. First, it was the working fluid was not water but silicone oil. First, and second, it was the overall temperature drop. So actually, the temperature drop across the film itself was probably 6 or 7 degrees or something like that. Okay, and it was not evaporating or boiling. Okay, anyway, and V, this is the mean velocity in the x direction. Okay, in millimeters per minute. Okay, not really supersonic. Well, anyway, okay, so they fixed many things, and now they varied the delta T and measured the net flow rate, and it turned out that at some temperature range, okay, the V was negative meaning going in this direction, and then it actually changes its direction and goes up above 0, which means the net flow was in the right direction. Okay. So once we became aware of this work, we started thinking exactly in the same direction. So we said, okay, so that's exactly, or probably exactly. This is experiment, no theory is involved. They didn't have any explanation. And actually, when I met Howard Stone maybe a year or 2 ago, he said, "Oh, I didn't know that anyone follows our experiments because nobody did any theory before." Anyway, we said, okay, actually I said, okay, so this might be a good problem for PhD for one of my students, but you know, sometimes, sorry guys, sometimes students are slow. You know, they have lots of things to do, teaching, girlfriend. So it takes time. Anyway, so in the meantime, we decided to solve similar problem, but a simpler one. Okay, and this is the problem. Imagine we have a bilayer system sandwiched between two horizontal planes. Actually, it's not important that they are horizontal because gravity, due to many factors, we'll discuss this later, gravity is not important. Okay, so basically two parallel planes. Do you see any of these? Okay. Okay, so okay, one is here, one is here, and what we have between the planes is actually a system of two fluids. One of them is liquid here, and the other one is gas here, and with all bunch of properties, density and viscosity, and climatic viscosity, and thermal diffusivity, and there is a thermal conductivity somewhere. Okay, and there is of course surface tension in between. And of course the geometry of the system is given. Okay. Now, of course we assume the simplest possible, simple Newtonian fluids. And now we want to heat in one of these planes. And we heat the lower one, actually on, well, it doesn't really matter whether it's lower one or the upper one, but on the liquid side. Okay, so, but we hit it in a non-uniform way. In which way? We assume that the temperature here on this liquid side substrate is non-uniform. It goes around a certain temperature which is called TW0, and we assume that TW0 is larger than T0, which is the temperature of the ceiling. And it has some deformation. Okay, so the deformation is of the amplitude amplitude A and multiplied by TW0, and this deformation, it has sinusoidal form. Of course, you can do any kind of function, but we started with sine. We like it the most. Okay, and this sine has this kind of structure, which means it's a wave. That's why we call it thermal wave. Okay, of a certain wavelength, L, and we impose a possibility of for this thermal wave to move with a frequency omega. Sometimes omega is 0, meaning that the thermal wave is standing, and sometimes, most of the times, it's omega is non-zero, so it's moving. And as I said, we assume that delta T, the temperature drop across the system, which is the difference between TW0 and T0, between the temperatures, the mean temperature of the floor as the temperature of the ceiling, it's larger than 0, so there is some potential of doing something interesting. Okay, so I think, and please correct me if I'm wrong, I think I don't need to introduce the main player here, Marangoni effect, so I can safely omit this, this stuff. So, okay. Which way do we go? Here. Okay. So basically, a Marangoni effect is present here. And because of the fact that delta T is actually positive, so the Marangoni effect has a potential to induce some flow and to do some interesting effects here in this system. Okay. And it may, of course, cause instability of the system. Okay. So now we were thinking about a theoretical approach. But it turned out that, well, a natural theoretical approach here is definitely to use long-wave theory, of course, if basic assumptions are satisfied. But then you realize, after you sit down and spend a few hours just deriving of all of these equations, or first writing the equations of the boundary conditions, then you understand that it's hard to make a progress here without making any assumptions, any additional assumptions, which sometimes they may look sort of questionable. For example, one of the assumptions made here. I know what. Let me. Okay, I will not say it now. In a minute. Okay, so you start working out all these long wave theory things. So what you are saying is the following: that the mean thickness of the liquid and the gas layer is much smaller than the typical wavelength of the disturbance. Well, that's okay. It's nothing wrong about this. By the way, I must say the following, that if you have a problem which doesn't have a typical wavelength in this direction, for example, think about a temperature on the floor, on both floor and ceiling, and the temperature is uniform. So in this direction, you don't really have a natural wavelength. Okay? Once you impose a thermal wave like this, or maybe different, a functional form, but you have a wavelength of the imposed temperature, so then you have, in the x direction, you have a natural wavelength, which is just a wavelength of this thermal wave. You can change it, you can play with it, you can make it larger, make it smaller, but you have a natural measure in this direction, natural scale. Okay? So that's why it's not a big deal just to assume that this epsilon to be much smaller than 1, and then you do all of these scalings, which are absolutely standard for long wave theory. Nothing is new here. And now you start making your assumptions. Well, first is the system. You want your system to be not far from equilibrium, and I will come back to this assumption. Why you want this? Because if you are far from equilibrium, which is just heat conduction across the system, okay, and then if you are far from it, so then you must think what to do with that advection, which is there, okay, order 1 Reynolds number effect. Okay, because if you have them, well, you are in a problem how to proceed, okay, because something is not working well. So I want to make this assumption, and we'll come back several times to this assumption in the next hour. Okay, now the next assumption, no gravity. Well, no gravity, well, you say, okay, you fly to some other planet, do your experiment. Fine. Or you make your system small. Okay, if it's very small, and you will see what we made up our test case is for the system, which is 0.1 of millimeter for the liquid and 0.3 of millimeter for gas. Gravity is not really very important, and definitely buoyancy is not there, because once you are, at least for water, below 1 millimeter thick, okay, so you can forget about, safely, you can forget about buoyancy and deal only with the Marangoni effect. Okay, so this is certainly not a problem.
Sorry, Alex.
Yes, please.
Do you mean buoyancy is not important, but gravity still yes? So the
No, buoyancy is not there, but we don't have gravity, because actually we did the same for gravity. Well, gravity, it changes numbers, but nothing important. I mean, instead of 5, you have 6, right. Something. It's minor. But you can put it safely there and just, okay, rerun this. Numbers will slightly move. Okay, and now this is the crucial assumption, and I will come back to this again and again. Well, it's not an assumption. We know that the viscosity of liquid is certainly much higher than the viscosity. We can think about the following, that the dynamics of the liquid, of the barrier system, can be, or the dynamics of the liquid phase and the gas phase can be effectively decoupled. Decoupled means you don't need to solve them all together and then you have a problem. Okay, but you can say, okay, they don't hear or didn't hear about each other, and the only remembrance, the only remnant of this interaction, of this coexistence of these two phases is just heat conduction in the base state. Okay, this is also, I must say, this is questionable in general terms. Okay, so that's why you see theoretical approaches, not approach, and this is just number 1. So that's why we come back again and again to the necessity of bring an independent expert, second opinion, and ask him whether you are okay or not okay with absolutely different tools. Okay, so we'll come back to this later. Okay, so in this model, the thermal problem is coupled. So at leading order, or at least at the equilibrium, or not far from equilibrium, still what's prevailing is that just conduct a conduction across the layer, across the bilayer system, and then it's easy to solve for temperature field in both phases. And then, once you do this, and once you decide that there is a decoupling between the two phases, so you can proceed, but then again, don't forget to ask for a second opinion. Okay. Okay, now the parameters of the Prof. First, let me introduce this guy. This is dimensionless frequency of the thermal wave. Okay, so this is omega, remember capital omega, this is the frequency of the wave. So small omega, lowercase omega, this is this guy, okay, dimensionless in thermal time units. It's shown here, and the basic assumption will assume that it's small. Okay, this is of order epsilon. Why? Because if you are either faster or slower than epsilon, then you can. Okay, remember we spoke about. I think it was on Monday when we spoke about scaling through this kinematic boundary condition. So now you have an additional time, and you want the time scale due to the movement of the or propagation of the wave to be the same, so that's why you must assume that it's order epsilon, otherwise it will not work. At least in this way. And then we have the whole bunch of parameters. We have, okay, let me start for a change from the left. Okay, we have a geometrical parameter delta, which is just the ratio between the thicknesses of the film. And then we have a Prandtl number, a Marangoni number. By the way, okay, F, this is a subscript for for liquid properties, and G is for gas properties. Okay, so most of the things are scaled with the liquid properties. Like Marangoni number is expressed via delta T, and delta T, this is the temperature drop between the mean temperature of the floor and the temperature of the ceiling. Okay, H. Think about it's sort of bilayer Biot number, sort of Biot number, which comes from the continuity of thermal flux through the interface. Well, delta is definitely incorporated here, or 1 over delta, so you can look at this H as just a ratio between the thermal conductivities, but it's also at the same time sort of Biot number, bilayer Biot number. Okay, and this is C, we all know it already, it's inverse capillary. Okay, and then we introduce one new guy, omega bar, and this omega bar is just order 1, sort of cousin for this omega, so it's just omega bar is just epsilon to minus 1 omega, omega is order epsilon, so this omega bar is order 1. Okay, and then we assume, again, we have to assume that the capillary effects are there, and we assume that the inverse capillary number is large, as 1 over epsilon to the third, and we assume that the Marangoni number is also large, as is of order of epsilon to minus 1. Okay. Fine. So, okay, so now a few details. Well, basically, as I said, use asymptotic expansions along the guidelines we discussed the other day, and then at leading order in epsilon, you have the thermal problem, which is conductive across the layer. You find everything, the solution is just a piecewise linear function in Y, no big surprises here, and the temperature at the interface you want to calculate it at Y equal H. H again, that's the location of the interface between the two faces. Again, it can be corrugated, it can deform, and it vary in time and space, and the interfacial temperature you get in this form where all bunch of parameters are present here. Let me remind you, okay, A, this is the amplitude of the corrugation of the temperature wave, and this F tilde function, this is the sine. But basically, if you don't like sine, you can use cosine, so your F will be cosine, always. Some other function. And then, finally, after some time, you get the evolution equation in this form. Again, subscript for x is just a derivative, partial derivative with respect to x. Then it's more convenient to rescale it back to the physical prescale quantities, and then finally you get this evolution equation you want to solve, and this, okay, now it's not f tilde, it's f hat, this function for the new variables psi, which is sort of x, and tau is sort of tau. Okay. So we want to work with this guy. I'm sure that you recognize this guy from the previous talks. Well, this one looks a little bit different. By the way, if you take a to 0, so then you get back the equation which was derived by Ivan Hoop and Sweeney, and Schatz, all of this, McCormick, all of these people, JFM 1997 or 8 or something. Okay, so we want to solve this equation and to see what happens. We want to solve this equation, and now with periodic boundary conditions in long periodic domain. How long is long? I will tell you next. And with initial condition, look here, flat. So actually, you can start with a corrugated initial condition, but actually, if you substitute a constant initial condition here for A, which is non-zero, so it's not satisfied, so it will evolve. Okay, so that's why we begin with a flat initial condition. Okay, so basically what we are interested in, it's not in the time and space evolution of the interface, but we want to get some profits from here. For example, like what we want to, basically we want to know what could be the interfacial velocity in the x direction, for example, but that's easy because once we know h at every time, at every spatial point, so we can calculate this, use this expression and calculate the interfacial velocity. And the most important thing is this q guy, and this q, that's mass flow rate in the x direction. So again, once we know this, so we can calculate this and see how it evolves and how it behaves. And this will be the main thing here, among others. Okay, so I spoke about some questionable assumptions which allowed us to derive the equation and to carry out the analysis, but then we say, okay, well, I hope I delivered the message. There are some questionable assumptions, so you want to check whether you are far away from the reality, or you are next to reality, or you are a reality, and the rest is just fake. So you want to see. Okay, so that's why we venture into this terra incognita of solving numerically Navier-Stokes equations with the heat equation, with the energy equation. Okay, and then okay, so we have this continuity equation, the Navier-Stokes equation, and the heat equation, and now they wanted to use VOF method, so you have to put somehow surface tension, but surface tension it's not a function, it's sort of functional, which is defined only along the surface, and the surface is a part of solution itself. So this method actually gives you or prescribes certain way how to do this. So there is a fake functional which appears here, okay, as a body force, but this body force is sort of concentrated along the surface. You see this delta function S delta function along the surface, okay? And of course, this is fine as long as the deformation of the surface is not very big. Once you get very close to rupture, so you have a very large deformation, so then it becomes to be questionable. It becomes to be sort of, you have to put many more points there to resolve the numerical issue, and sometimes it may take a long time. So every method has its limitations and its benefits, advantages, disadvantages. That's all life is about. Anyway, okay, and using VOF for tracking the location of the interface, you introduce some function which is normally called color function, which is 1 at one side of the interface, 0 at the other side, and you try to solve all of this, and that's what you do. And this will be a sort of second opinion to compare with the predictions of the long wave theory. So we'll come back to this later. Okay, so this is the bilayer system which served us as a test case. Okay, so liquid is water. In the previous version of this file, which means yesterday, it was liquid water and gas water. Okay, so I changed it. Okay, so gas is air. And, well, the bunch of properties here, but the most important thing is that the thickness of the liquid layer is 0.0001 in meters. Okay, so it's just 0.1 of millimeter, a very shallow layer. And the gas, which is also important, it's 3 times thicker than the liquid. Okay. And a list of properties which are not really important now. Okay, so now the question is, we are going to explore what happens with A, which is non-zero, which means the temperature of the floor is non-uniform. What happens? Let's first talk about the uniform case, okay, just for reference. Okay, so what do we know? We know the following thing. Okay, if the parameter set for our system corresponds to linearly stable case, so then life is simple. Okay, you have a disturbance, it decays. After some time, you come back, you see everything is flat, nothing to write home about. Okay, so this is a trivial. Second, if the parameter set corresponds to linearly unstable case, now it becomes interesting. So then it evolves. Now the question where it evolves. And it turns out that if A is 0, so the film ruptures at some time, okay, at some later stage. So somewhere in the periodic domain, at some time, local thickness becomes 0 or next to 0. Actually, in this case, it will be 0. By the way, much faster than in the reality error case, much faster than on the cylinder. We said that it's possible to prove that that's infinite. Here it's finite, just because of the fact that, that's for the mathematicians, the capillary ligature, the one with the fourth order derivative, it's proportional to h cubed. However, the driving force for instability, which is Marangoni, is proportional to h squared. Okay, there, remember, both of them were h cubed, so they were sort of equilibrated for small h. However, for this case, h squared is larger than h cubed for small h, so that's why it will drive it faster toward rupture, and the rupture, it may be proven, it will occur at the final. But anyway, so now we have a competition between whom and whom. There is a tendency to rupture. And now the question is, if the film wants to rupture, it means somewhere the local thickness will decrease. Okay, where will this water go? It will go somewhere else. Okay, so somewhere at the expense of this decrease of the thickness, somewhere the thickness will increase. Okay, so now we understand that if there is a sort of a finger going down, for example, like this. Okay, so this is the beginning of the story. So now it moves toward rupture, something like this. Okay? Now the question is, if you remove liquid from here, so it goes to this side and to this side, so these guys become fatter. Okay? So there is a competition between two factors. On one hand, this guy wants to go down, but on the other hand, this guy wants to go up. Okay, so it accumulates liquid removed from here. So now there is a competition between rupture down and rupture up. Okay, rupture down means the local thickness of the liquid film will be 0. Or if this one goes up faster, so then this one will, okay, touch with its head the ceiling, so the gas layer will rupture. So the competition, okay, who is going to rupture first? Okay, so that's why I wrote there. And actually, what we would like the system to disallow rupture up. Why? Because, as you will see, I will bring water to the thin locations and will sort of replenish these dryish spots. And so we don't want this guy to rupture up, because then the evolution will stop and we'll need to run it again for a different set of parameters. That's why actually the gas layer is 3 times thicker than the water layer. It doesn't go. It always wants to first rupture up, rupture down and not rupture up, so it can continue forever. Okay. Yeah. And now, if you carry out your weakly nonlinear analysis still for the case of A equals 0, okay, you carry out your weakly nonlinear analysis, then you find that bifurcation is supercritical. Subcritical. Now, for subcriticality, it's again, I mean, your equation is, for the amplitude, is something like this, epsilon A plus some mu A squared A, and mu is larger than 0 and epsilon is larger than 0, okay? So you are linearly unstable and you don't have saturation at the nonlinear stage, at least at the cubic level, okay? So it means that actually the amplitude of your solution wants to increase. Again, going in the same direction when you increase with time. When you increase the amplitude, so it means either you will remove fast the liquid from, take it from somewhere, from the thin spot, and then it will rupture down, or you accumulate liquid so fast it will touch the ceiling with its head. So they go in the same direction. No, I didn't want to. So that's how it works. It goes by itself. Anyway, I revealed the secret. Okay, fine. Okay, so let's start this numerical investigation of this system. I would like to begin with the simple case. What is a simple case? Simple case is when for A equals 0, the system is linearly stable. So which means if A equal to 0, nothing happens, you make a disturbance, go home, you come back, nothing happened, everything is flat and quiet, and it's boring. Okay, so this is the case I would like to begin with, but now, okay, A is non-zero, okay, so it's not that trivial. Once A is non-zero, so what you have, this is the temperature. It works? Yes. I didn't see it.
Yes, you see the set line. Now okay.
Well, it's somewhere anyway, and let me press, it will hit somewhere. Probability to hit a certain point is 0, but it hits somewhere, so you look there. Okay, fine.
Just to attract our attention.
Yeah, exactly. Just to make you looking for this spot. Okay, anyway, so this is how the thermal wave looks like. Okay, A equals 0. Sorry, A is non-zero, but I want to start with a static thermal wave, which is omega equal to 0. Okay. So the thermal wave will be static. It will look like sine. You want the sine, it will appear like sine. And what you see above, this is a typical solution coming from the Navier-Stokes equations. Typical solution showing the flow field and the shape of the interface between the gas phase and the liquid phase. And this is a steady state. So, for some value of this, now see, of this A is 0.1, not very large deformation of the temperature in profile, one number is 100. Okay, L is 25, it's not exactly 25. Okay, every value for L you see, you have to multiply by about 8. So this is actually 1 to 200. This is the system for the liquid layer. Okay, so liquid is 1 in these units. and the length is 25 times 8, so it's 200 times larger than the thickness. Okay, so it's a really long system. Okay, so what you see a steady state, which system, the system comes at, and that's how the surface, the interface separating between the two faces looks like. Now, is it logical? Yes, it's logical, because see, here the temperature is minimal. If you have minimal temperature at somewhere on the floor, okay, so if this is not far from conduction, so the temperature here at the interface will be lower. Now, if it's lower, the surface tension is higher. Okay, if it's higher, then okay, here at this location, the temperature is higher, so the surface tension is lower. So there will emerge a shear stress pumping water from in the direction of the surface gradient of surface tension, which means from the lower surface tension location to higher surface tension location. So it will take water from here, it will bring it here, pile it up there, so that's what you see. But in addition, what you see is the following. By the way, I forgot to introduce the colors. So the color code is actually the opposite to the intuitive one. Why? Because it looks more photogenic. So the brighter colors are they correspond to hotter temperature, to higher temperature, and darker colors correspond to lower temperature. Well, just to make fun of it, but it looks better. Actually, I don't know why, but we checked it, and that's what we found. Anyway, another feature of this field. See these green lines? Okay, now I see. Okay, here, the green lines. So it turns out that the whole flow field broke up into several pieces. Okay, in this piece, within here and here, so there is one vortex going in the fluid, in the liquid phase, one in the gas phase, and exactly in the direction along the surface. It goes from here to here, so it goes like this and goes back, and here again it goes like here and goes back, and the same on this side, and on this side just a periodic extension of one another. And what's most important, this is a steady state. Okay, so you can create non-trivial steady state just by imposing static thermal rate. Okay, so it's not very exciting, but nevertheless. Okay, so now again we want to check what happens with first we know that this the final destination is a steady state, but now we want to see what the both models give us. Okay, so the convention from a convention from now on will be the following: the solid curves correspond to the Navier-Stokes, and all kinds of broken curves will correspond to the long wave approximation. Okay, so for example, okay, let's begin with this. Okay, so what do we see here? We see here the interfacial shape within one period coming from, we said it's steady state. Okay, it's exactly the same. Thank you. Okay, so it's exactly for the previous case which I showed you with this colors. Anyway, this what you find from the Navier-Stokes, and this what you find from the long wave theory. So there is well, a good agreement. After all, long wave approximation is approximation. We would not expect that the approximation is exactly the same as the original, because otherwise you would say, okay, so the approximation, this is the real thing, and the rest is not important. Okay. But again,
what is the aspect ratio to compare? What is the aspect ratio to make a comparison? For Navier-Stokes,
here it's 1 to 200. 1 to 200. So this was actually, you see, I mean, you have to, nothing in this life is for free. In US, people say there is no free lunch. I mean, moreover, nothing is for free. Okay, so if you want to solve Navier-Stokes equations, so well, you have a certain accuracy, and so there is certain extent when you can solve your equation, because otherwise, if it's not 1 to 200, 1 to 5,000, so then you put many more points, and then you count years before you get your solution back. So that's the thing. Anyway, so this is difference in the maximal, I think it's somewhere around 7-8% in the deformation. But again, I mean, this is also steady state, so they look pretty much similar. Now, this is temporal, so we still want to sort of to check our intuition and to compare both the methods just to see what we get. Here, for example, we show you the temporal evolution of several things. First, okay, H max, the maximal thickness of the film. These are these guys. Well, that's exactly. I mean, finally, they go to the same difference. This is the minimal thickness of the film in both models, and this is delta H, which is the difference between the maximal and the minimal thickness. So they go quite well. Well, sometimes at some stage they separate. And by the way, we didn't show here, but basically on this curve you can test actually your linear stability theory. So from some time up to here, they were exactly the same curves, and then they deviate because nonlinear effects took place more seriously. Okay. One more thing which is quite interesting for this static thermal wave case. Okay, so there are several parameters, as you may notice, for this problem. There is A, the deformation of the temperature profile. There is a Marangoni number, of course, the main hero here, and there is the length of the wave. So I want to see which one derives in which direction. Okay. So, for example, here, do you see it? No. No. Oh, somewhere. No, it's probably the battery is low. Well, here I can see it because it's dark. There.
Ah, no. Did you see?
Well, I press, but it does something else. Well, anyway, the upper graph. The upper graph shows the deformation of the film at its steady state as a function of the Marangoni number from 0 to 1000, and where, okay, L is changing, which means, okay, A is fixed. So you have a certain deformation of the temperature profile, and now you see what happens with variation of the wavelength of the thermal wave, and when Marangoni number is changing. So what you see first, well, if you fix L as well, so the deformation, well, it goes the right direction. The larger is the Marangoni number, so the larger is the deformation. It's kind of expected, I would say. But what is not expected, okay, so for example, the red curve, it's for smaller n. N equal 10, it means actually 1 to 80. 1 to 80. Okay. So it goes like this, monotonically, but then if you switch to 15, 15 is 120, okay, even slightly more. Okay, so then it's again the same behavior, but it stops somewhere, see? I look first at the curves, and then the symbols are from the long wave theory, okay? The curves are coming, or the field symbols are from the Navier-Stokes. So it stops somewhere. At 400, for example, the blue curve stops, yeah, right here, now I see, okay? Okay, around the deformation of 1.6, okay? And we did not continue this. Why? It's not the fact that we were lazy. Maybe we are lazy, but not in this case. Why we stopped it? Because the film ruptured. So for the given length of domain, if you increase the Marangoni number, so what it happens, it behaves like, okay, A equals 0, okay, so it wants to rupture, and it ruptures. So because you create such a large deformation of the temperature, so the stress becomes so big, it drives water out of the location of the higher the temperature, and then it breaks everything. Now, if you increase L even more, so you see the behavior is the same, but it stops earlier. Stops earlier because you have a larger domain, so you have more flexibility for your film. Imagine if you have a ruler made not of wood but of some flexible material, metal, for example. You press it. If it's a short ruler, so it will remain straight. But if it's longer enough, okay, so then it will buckle. So it has some more action to be taken within a certain domain. That's exactly this. Okay. So now let's look at the lower graph. So the lower graph shows us the deformation of the film when one body number changes for different A's, but for a given A, for a given length of the periodic domain. Again, it's the same story. The deformation increases with the Marant body number, but for smaller A, it increases slower than for larger A. You have larger A, you bring not a little hammer, you strike the film with a big hammer, so then it will deform more and will break earlier. Okay? And again, I mean, the deformation is about 1.6 before breakage. Okay, so there is some interesting feature of this number, at least here. Okay, so now a more interesting case. Okay, a propagating thermal wave. Okay, so now when we think about the propagating wave, think about the following. We move the thermal wave. So the location of the minimal temperature, for example, on the floor, it's moving. Well, actually everything is moving. Okay, but let's follow the location of the minimal temperature. It's moving. Okay, when it's moving, so the temperature is minimal, the surface tension is maximal. So this is the location which will attract the water from the neighbors. Okay, so if we move this guy, so definitely this location will also be moving. Okay, so it will follow somehow this, because this is the source of your activity here. But definitely the liquid will not respond immediately. It will respond after some time. So the point is the following: there should be, and there is, some phase lag, which we call delta phi. Okay, and this is the phase lag. This is the difference of the distance between the location of the minimal temperature and the maximal deflection of the film interface. Okay, and we'll follow it, we'll measure it, and we'll see some very unexpected properties of this value. Some of them we cannot explain. We see them clearly. You will see them very shortly, but we cannot explain. We cannot solve analytically, because it's far beyond any possibility to solve anything analytically. Anyway, I will come to this later. So this is a typical example when the system for A equal to 0 is linearly stable. Now A is non-zero, omega is non-zero, the thermal wave is propagating, and this poor guy interface, it follows it, and we say that there must be some phase lag, and there is phase lag. Now, if you look here, you look at this structure of the flow field, again, the color convention is the same, is counterintuitive in the same way like in the previous one. Okay, so the brighter shades are higher temperatures and the vice versa. Okay, so again, this is now the interface. Looks like this. The maximum location is somewhere here of the interface, the maximum deflection. This is the location of the minimal temperature. This guy is also moving. Now, again, the flow field sort of disintegrated into several vortices. Now, one vortex in the liquid phase, one vortex above it in the gas phase, but the whole thing is moving now. Okay? So these green lines, oh, very good, thank you.
Let's keep together first, like the point.
Ah, okay, so I must, so it's like a joystick. Okay, so now I have to compete with my children. Okay, fine. Do you see?
The yellow one.
Oh, okay. So it's no wonder I don't see it. Do you see it now?
Yes.
Oh, okay. Yeah. Okay, fine. Thank you, sir. Thank you. Okay. So the flow field disintegrated into vortices, but these vortices now they are moving. So these green lines, they are moving. So this vortex system is moving, propagating in the right direction, following the thermal wave. Now, if you ask me what happens with this solution and with the others, they look like traveling waves. They look like, which means they, well, if I put one on top of the other and shift them and pile them up to check whether it's the same shape, well, if I close my eyes, both eyes, they are definitely of the same shape. When I open one of the two, well, there is some noise. Now, this noise, it looks like, well, and then you ask, okay, whether this noise is sort of random, maybe numerically induced, or maybe not. It doesn't seem to be numerically induced. So it has some coherence with when you perform FFT. So you see that one of the peaks corresponds to this omega, and then it says, well, it's related to this forcing. But this noise is very small, and it doesn't go away when you increase the accuracy of your computation. So which means it's nearly traveling wave, but not strictly speaking. Okay, now which ones? Okay, now the same case, a propagating thermal wave. So now I would like to see the following. Now I have okay, omega in my hands, another control parameter. So I would like to move waves faster and faster and to see what effect I get. Okay, so this is the graph showing us again interfacial shapes for both Navier-Stokes and long-wave theory in one period, and interfacial shapes for different omegas, different speeds or different frequencies of a thermal wave. And again, solid curves are for Navier-Stokes and dashed curves are for long-wave theory. Now, what we do, we shift these waves because they are propagating. Okay, so just for a comparison, we shift them. I forgot, but definitely I think it's written here, or maybe not in the paper. Anyway, we shift them in such a way that the maximum of the temperature profile is at 0.75, somewhere here. Okay, just to align them, to see what happens. Okay, so what do we see? For this blue guy, omega equals 0, this is Navier-Stokes, this is long wave theory. Well, again, I mean, there is some 8-9%, 7 to 9% difference, which is not really big, but well, it's substantial. But the sort of qualitative analysis, or the results of qualitative analysis, are always the same. Okay, now you start moving this guy faster and faster, so you go from this one to the red one. Okay, what is the main feature? The height decreased. Why is that? Well, because you move your film. You move your thermal wave. The film is moving after it, but because of the fact that you bring water to bad locations, to the desert, okay? So you put more and more water, so it doesn't want to rupture anymore faster. It wants, but it cannot, okay? So that's why it doesn't go deeper, so this guy doesn't go up, okay? So that's why it goes like this, okay? So the minimal thickness, of course, goes up and the maximum goes down. And again, going from the red one to the green one, it's the same direction, but the yellow, yeah, and finally for large, well, not large, but for larger value of 0.18, I will comment a word or two immediately about that. It's almost flat. It's not flat. It's about 2% of the mean thickness. Okay. So now don't forget. You may ask why I didn't use omega equal 5. Okay. Remember, remember, omega should be small, order epsilon, okay? So 5, not exactly order epsilon. Maybe, but not always. Anyway, okay. Now, this is the interfacial velocity, and this is also a very important factor here. The interfacial velocity, which means along the surface, in the x direction. Okay, so for omega equal to 0, this is the guy. And again, the correspondence, look, is quite nice between the two. Okay. Now, what happens if you move the thermal wave faster? What would you expect? The interfacial velocity will increase or decrease. Of course, basically the amplitude definitely should increase because you move it faster. So somehow it must follow it. So you move the thermal wave faster, so the wave will go faster. Or sorry, the liquid will flow faster. Okay, it doesn't mean that the wave will go faster, but the velocities will become higher. Okay. Now there is one interesting thing, I should say, not the most interesting, but one of the. Look at the graph, this graph, which shows you the flow rate with respect to omega. Now the flow rate, remember we defined the flow rate. Now the flow rate is a function of time and x, because it's local. Now to make some integral value, we integrate it. So we have function of actually time here. This is a net flow, so to speak. Okay, if you have EQ non-zero, so it means something is moving, something is flowing somewhere. Okay, so this is Q as function of omega. Now this is a function of tau, of time, so we wait until everything is equilibrated and then we measure it. Okay, fine. So now, okay, omega is changing and for different values of the Marangoni number. Now, what happens is the following. For sufficiently smaller omega, the flow rate goes up. For sufficiently larger omegas, it goes down. Okay. Actually for every Marangoni number. Why is that? Well, the hint is exactly what I said. On one hand, if you move omega faster, if you go to larger values of omega, what you have, the velocities increase. Okay? However, when you go to larger value of omega, the film flattens out. Okay, so now if you have a larger cross section, so you you have a faster flow, so you can bring more fluid. But if you have a thinner film, so you cannot move more liquid because there is no place to go. Okay, so which means there are two competing factors here. Okay, which compete, and that's exactly what you see. There is a distinct maximum for this flow rate with respect to omega. Okay. Okay. Now, and by the way, the field symbols are for Navier-Stokes, and the open symbols are for long wave theory. Look, fine differences. There are some, but not really explicit. Anyway, now let's move to a different thing, which is the phase lag. Okay, remember we spoke about phase lag. There should be some retardation of the response of the interfacial wave with respect to the thermal wave. But there is a response, and that's how it looks like. It goes like this. Now, in this case, well, Marangoni number doesn't, at least in this range, doesn't have any pronounced effect. So, which means that these phase lags are almost the same. Actually, Navier-Stokes and long wave theory on one hand, and when you change Marangoni number in this range, nothing exciting. It happens, you collapse almost on the same equal. But there is one interesting feature, which maybe here it looks trivial, but nevertheless we will see it later on as well. Look at the location of the maximal value of the flow rate. It's here for this value, here for this value, here for this value. Here, for example, you see there is some difference, some shift between the Navier-Stokes equations and the long wave theory. There is a little shift in difference in numbers, of course, but there is a shift. But nevertheless, when you look at the location of the maximum flow rate, fix and check the location in terms of omega, and then look down and check what is the phase lag for the given omega, which is associated with the maximal value of the flow rate, you find a very exciting phenomenon, and it's the following. For the Navier-Stokes equations, it turns out that the phase lag corresponding to the maximal flow rate is about, okay, we measure it in the units of pi, delta phi divided by pi, 0.3. So if you take this, go down, so it's somewhere here, 0.3. For the long wave theory, it's somewhere 0.35. So which means, well, if you want to compare and say, okay, I have two close values, what is in the middle, it's about 0.33, and it definitely must be 1/3 of pi, okay? So, well, here it's a little trivial in the sense that, okay, all of this, it collapsed in the same, on the same curve, but next you will see a totally different thing. It corresponds exactly to somewhere between 0.3 pi and 0.35 pi, and this is quite exciting. You ask me why? I don't know. Okay, well, it's lesson. Okay, so now, well, it's still propagating wave, but now, well, different values, different parameter values. Again, the flow rate for different values of A for a larger polynomial number. Now it's 400, but the domain is shorter. Here it's 10. 10 means 10 multiplied by 8, it's 1 to 80. Sufficiently long. Okay, so what do we see here? Here, well, now we see a discrepancy here, for example, between the two theories. And here, starting here for two theories, well, here it's less pronounced. Now, yeah, but otherwise the existence of the maximal flow rate is there. It's a little in different location, but it's qualitatively it's the same. Now I want to ask two questions. First, why is that a discrepancy occur? This is the first. And second, how I'm with respect to this 1/3 of pi. Okay. So first, why is there a discrepancy? And I think the answer is absolutely clear. Look at the values of this omega, where it occurs. It occurs somewhere here. 0.8, 0.75, somewhere there. Okay. So what was the basic assumption for omega? Omega should be small, or the epsilon. Okay. So I would not expect the one-to-one agreement for larger omega. Okay, so how large, I don't know. How large is large, I don't know, a priori. How small is small, I don't know. I have to look. Okay, so for this case, it seems that 0.75 is probably not so small value, so that's why there might be, not there is, but there might be a discrepancy. So there is a discrepancy. I would not expect this agreement, a very good agreement, to be up to infinite value of omega, because somewhere they should deviate, because otherwise what's, I mean, how come the approximation works forever? It may, but it's kind of, it leads to sort of brow lifting. Anyway, there are certain distinct value of maximal value of the flow rate. Now you look at the location of this maximum, you find yourself at 0.3. For Navier-Stokes, 0.35, somewhere in that range for the long wave theory, and again you are around 1/3 of pi. And now, when you look at the deviation here for the phase lag, so the phase lag seems to be more sensitive toward this between the original equations and the approximation. So you see the deviation starts somewhere here, 0.2. Okay, so that's logical. Omega larger than 0.2. Sometimes it's small enough, sometimes it's not small. Sometimes you read books like by Naife, for example, asymptotic analysis, and then you see some asymptotic expansions for small for small epsilon, and then the guy says, okay, let's assume epsilon equal 1. Okay, and let's solve. Okay, so 1 sometimes is small, mostly not that small. Anyway, with respect to time, it's still monotonically going in that direction, right? It's what, 15 minutes or something like this? At 10 minutes? Okay, so let me increase the speed going to larger omega and talking supersonic. Okay, so basically this is the clue. Omega should be ordered with epsilon, so you should not expect a very good agreement for larger omega. And again, similar case. Now here, okay, L is changing, and when you change the periodicity size, these guys become very, very sensitive towards all of these values. Look at the horizontal scale. The horizontal scale for omega is logarithmic. Okay, so it's even it's much more pronounced. So we see all of these guys are far apart when we change L for fixed A and the Marangoni number. But again, when you look at this maximal value, you find yourself again with 0.3 of pi, and it goes on and on and on. And again, the deviation, well, which begins somewhere here. In this case, for the flow rate, it's less sensitive because it's finally it's sort of integral value, so it should be less sensitive to all kinds of approximations. Okay. Okay. One more interesting thing before we move to the case of the linearly unstable system, which will be short, because we see all of the properties, or most of the properties here. Okay. Here we show the variation of the optimal value of omega, the one which corresponds to the maximum flow rate, with respect as a function of the wavelength. Okay. So all of these guys collapse on the same curve, except for this one. This one belongs to the long wave theory, and this one belongs to L equal 5. L equal 5 means the length of the domain is 40. So 1 to 40. Well, apparently for the long wave theory, 1 over 40, well, it's not that small. You cannot say a priori, but a posteriori you see. Okay, and then they collapse on the same curve. So actually this value is very insensitive to whatever, and the range for Marangoni number is between 0 and, no, well, actually between 0 to 1500, and very wide range for A, and they all collapse on the same curve. Okay, now let's look at the case of the linearly unstable case for A equals 0. Okay, okay. Now, again, this is a comparison between long wave theory and Navier-Stokes equations, but now it's for different omegas, and the Marangoni number is 2500. Now, let me tell you that for this parameter set, the threshold, the linear instability threshold is for Marangoni somewhere between 1600 and 1700. Okay, so that's why in the previous case we checked up to 1500, not crossing the borderline. So converticality here is large. And because of this, for some, especially smaller values of this omega, we see larger deformations. Okay, so it wants to go down, it wants to rupture, but you bring water, you don't allow it to rupture because you move it sufficiently fast. You put water in the desert, so it may live longer. So actually, these guys are also almost traveling wave, traveling with a certain speed, and the speed is certainly associated with this omega, actually equal to it. But there is a little oscillation, and not numerical oscillation up and down, and a little left-right. And it doesn't go away with improvement of accuracy. Okay, so what is interesting is the following. Again, if we increase the value of omega now, this, Now the competition between the two, which one will go? Okay, so with increase of omega, we get a flatter wave, of course. It's the same thing. But now let's look at the interface velocity. Sometimes it develops some kind of waviness, but it's not important here at least. Okay, the important thing is here. Okay, now we want to look at exactly the same quantities like the net flow rate with respect to omega, and
You just push.
more than one is many. Do you remember this? Okay, so now, okay, the flow rate is a function of omega, and the phase lag is a function of omega. Okay, now you see the field symbols coming from the Navier-Stokes equations. You see open symbols coming from the long wave field. Okay, in this domain, we were able to solve the problem for both. Okay, and the comparison, well, it's good to me. Well, here there is some deviation because we said the phase lag is a little more sensitive, stands for smaller values of omega. It's consistent. That's fine. But then, look here. It's not that they were lazy to solve the Navier-Stokes equation for that case. No. It turns out to be impossible. Why? Because the deformation is very large. So it goes almost to rupture, doesn't rupture. It's stopped somewhere for small thicknesses. But numerics for the Navier-Stokes equations fails. So again, there is no free lunch. You have a strong tool which doesn't have anything with approximation. You can use it as long as you can. If you cannot, you cannot. Okay? So that's why you need a symbiosis between the two. Sometimes you can afford it, and then you are in good shape. Sometimes you cannot. Most of the times you cannot, and then you don't know what you saw, in some sense. Okay, but so which means that if you start looking here and look to the left, well, I think it goes to the same place. So the comparison is good. How about here? Well, I don't know, but it may go this way. But look again here. This is the maximum flow rate. You land some again at about 1/3 of time. Okay, even for this case, when your base or reference system is linearly unstable. Just a few more things. Okay, so this is the case which they cannot resolve for with the Navier-Stokes equations, and look at the shape of the wave. Okay, so this is a time, this is 1. So this is, I don't remember how much is that, but that's in the range of 0.15 or something like this. So the deformation is already that large, so they cannot solve it with normal numerical accuracy. Okay, so basically these guys move to the right after the thermal wave. This is the interfacial shape. Okay, so you have these blobs, drops moving to the right. Now this solution, it has a very special value. Why? Because coming back to the motivation, we want to move liquid from point A to point B. Now, of course, you can say, okay, I have a gravity wave or a gravity capillary wave which runs. At some stage, it started there, it will reach there. That's absolutely right. But not the same guys will go there. So most of the guys, actually all of them at the interface, they do something like this. Okay, they just send a signal, but they don't go there. Somebody else goes there. Okay, nobody actually goes there. Those who stay there, who live there, they will stay there. But here it's different. Why it's different? Because you trap liquid here in this droplet. And then it's a periodic structure. And then you trap the liquid. There is no flow rate through these tiny liquid bridges. Okay? So you trap the liquid, it circulates inside the drop, but the whole drop train moves in the right direction. So it's the other end of this long table, there is a guy collecting the drops and says, okay, thank you very much for sending, send me more, and then you have a constant supply of these guys. Okay. And I think it's almost the end of the story. Let's skip this and just go to the summary. Well, first, it's possible to induce this kind of motion. We call it thermocapillary pumping of liquid using thermal waves, and actually along the substrate. And so pumping results, this thermocapillary pumping results in a non-zero flow rate along the substrate. And there is an optimal thermal wave speed for which you get the maximal possible flow rate in the x direction for a given set of parameters, and to the great excitement of all of us, the maximal flow rate corresponds to the phase lag of about 1/3 of pi, and actually comparison between the full Navier-Stokes equations and the log wave theory shows to be a very good or sufficiently good for any purpose. After all, don't forget this is approximation which makes everything much easier than just to run to the computer and to ask for a favor, please solve me Navier-Stokes equation. It takes a long time, but the comparison is very good. Okay, thank you very much.